Welcome to Clean Tech Deep Dive.
I'm Jennifer,
And I'm Justin.
and Justin is here with me today. For this deep dive, you've given us a really fascinating collection of information. We've got your notes from today, April 21st, 2025, some Wikipedia pages covering things like wastewater treatment, the water industry generally, specific water treatment methods,
Yeah, good mix.
plus a detailed industry briefing, a learning guide with quizzes, which sounds interesting, and even a look at future water tech trends.
Right. So our goal today really is to give you a clear, hopefully engaging understanding of this absolutely vital industry.
Exactly. We want to maybe surprise you with a few key facts, but without, getting totally lost in the weeds. Cut through the complexity.
Yeah, precisely. Show you the essentials of how we get clean water and, crucially, how we manage it after we've used it. Think of it as your personalized guide to the system we all rely on.
Okay, so let's kick things off. When we talk about the water industry, what exactly does that cover? It sounds simple, but I bet it's broader than most people think.
You're definitely right there. At its core, sure, it's about supplying the water we need for, well, everything, daily life, business, industry.
Mm-hmm.
But, and this is key, it's also just as much about managing the wastewater we produce, treating it so it can be safely put back into the environment or maybe even reused. It's a whole cycle.
A full cycle, right?
No.
Supply and management. So within that big picture, what are the main sort of sectors or areas?
Okay, yeah, we can break it down. First up, you've got drinking water services, as it's termed in some context.
Okay.
This is purely focused on getting safe drinking water to people. It covers sourcing the water, which is
Taking it from rivers,
Yeah.
reservoirs.
exactly, then purifying it, usually
Okay.
at dedicated treatment plants, and finally distributing it through pipe networks.
Got it. So source to tap, basically. What's next?
Then you have wastewater services, or RCALN.
Oh.
This flips the coin. It's about collecting all that used water from homes, businesses, industries, transporting it via sewer systems, and then treating it at wastewater treatment plants. The main goal here is removing pollutants to stop environmental contamination. And this bit includes managing the leftover sludge, too.
Sludge management sounds like a dirty job, but someone's got to do it.
Definitely. So clean water in, dirty water treated and managed. What else fits under this umbrella?
Well, you also have industrial water treatment. This is quite specialized
How so?
because different industries need water of varying qualities for their processes. Think about making microchips versus brewing beer, very different water requirements.
Ah, okay. Makes sense.
And they also produce different kinds of wastewater, which often needs specific, tailored treatment before it can be discharged legally.
Right, you can't just dump industrial waste straight into the sewers. What about farming? Agriculture must use a lot of water.
It does. And that leads to agricultural wastewater treatment. This focuses on dealing with runoff from fields, which might contain fertilizers, pesticides, and also wastewater from livestock operations, like animal waste. So trying to prevent that from polluting rivers and groundwater.
Precisely. And there's one more specific type worth mentioning. Leachate treatment.
Leachate. What's that?
That's the liquid that seeps through landfill waste.
Mhm.
As you can imagine, it could pick up all sorts of nasty contaminants.
Oh, right.
Yeah.
So it needs its own dedicated treatment process to prevent serious pollution of the soil and groundwater around landfill sites.
Okay, that covers the main sectors pretty well. Now, zooming out a bit, what are the fundamental components, like the building blocks of the whole industry?
Good question. You could think of it in terms of maybe four key things. First, the obvious one, the water infrastructure.
The pipes, the plants.
Exactly, the physical stuff. Intake facilities, treatment plants for both drinking water and wastewater pumping stations, and yes, the huge networks of pipes delivering clean water and taking sewage away.
It's kind of amazing how much of that is just hidden underground, isn't it? Out of sight, out of mind until there's a leak.
Absolutely. Yeah. Then second, you have the operations. This is the actual running and management of all that infrastructure.
Who does that?
It varies. It can be public bodies, local councils, national agencies, or increasingly, it might be private companies.
Oh, okay. Infrastructure, operations. What else?
Third is the functions, or how it's structured organizationally. Sometimes you have integrated systems where one entity handles the whole cycle, drinking water, sewage, treatment, everything.
All under one roof.
Yeah. Or it can be separated. We have examples like in the Netherlands where cities might handle sewers, regional companies the water supply, and then special water boards do the treatment.
Interesting.
And Munich apparently splits it three ways. Integrated systems might be simpler to manage, perhaps, but separating allows for more specialization, though you need good coordination.
Different strokes for different folks, I guess. And the final component.
The final piece is the technology and equipment supply sector. This is all the companies that develop, build, and supply the actual treatment technologies, the pumps, the filters, the chemicals.
The engineers designing the plants.
Exactly. The engineering firms, the construction companies, it's a whole ecosystem supporting the frontline services.
Got it. So infrastructure, operations, functional structure, and the tech suppliers. That gives a good overview. Now let's get into the really interesting part for me. How is the water actually cleaned? The nitty-gritty of treatment.
Right. This is the core mission, isn't it? Clean, polluted water. Generally, treatment methods fall into three broad categories: physical, chemical, and biological.
Okay, let's start with physical. What does that involve?
Physical processes basically use physical forces to separate out solids or other particles. No chemical reactions needed, just physics.
Like what?
Well, the most basic is probably sedimentation or settling. Just let the water sit quietly in a tank, and gravity pulls the heavier solid particles down to the bottom.
Simple but effective for the big stuff, I guess.
Exactly. Then, for the finer particles that don't settle easily, you use filtration.
Running it through filters.
Yep. Passing the water through layers of sand, gravel, or sometimes specialized filter membranes. It physically catches the smaller suspended stuff. Think of it like a sieve, but for water.
Okay. And you mentioned phase separation earlier.
Ah, yes. That's another physical method, used specifically when you need to separate substances that don't mix, like oil and water. You exploit their density differences or immiscibility.
All right, so physical is about separating things out. What about chemical processes? I assume this means adding chemicals.
You got it. Chemical processes use added chemicals to cause reactions that remove or neutralize pollutants. Oxidation is a key one.
Oxidation, like rusting.
Sort of, but controlled.
Yeah.
You use oxidizing agents, chemicals like chlorine or ozone, to break down organic matter, reduce toxicity, and it's also a vital part of disinfection.
Okay. And I've heard terms like coagulation thrown around.
Yes, coagulation and precipitation. These are really clever chemical tricks. You add chemicals called coagulants, often aluminum or iron salts. These cause the really tiny fine particles, suspended in the water particles, that won't settle or filter easily to clump together.
So they kind of stick together.
Exactly. They form larger, heavier clumps, called flocks. And because these flocks are bigger and heavier, they can then be removed much more easily by sedimentation or filtration.
Ah, so the chemicals help the physical processes work better on the tiny stuff.
Precisely. And the last big chemical step, absolutely crucial, is disinfection.
Killing the germs.
Yep. Killing or inactivating harmful microorganisms, bacteria, viruses, parasites, to make the water safe to drink or discharge. Chlorine is common, but ozone and UV light are also widely used.
UV light, how does that work?
Ultraviolet light damages the DNA of the microbes so they can't reproduce. It's a physical method of disinfection technically, but often grouped here. No chemicals added.
Fascinating. Okay, so physical, chemical. What's the third category? Biological.
That's right, biological processes. This is where we harness nature, specifically microorganisms, to do the cleaning for us.
Using bugs to eat the waste.
Essentially, yes. A major type is biochemical oxidation, often called secondary treatment in sewage plants. You create conditions where microbes, either aerobic
Needing oxygen?
or anaerobic,
Not needing oxygen.
consume the dissolved and suspended organic pollutants as food. They break down the complex organic matter into simpler substances.
So you're basically farming microbes.
In a way, yeah. You manage the environment oxygen levels, temperature to keep the right kinds of microbes happy and hungry. And anaerobic treatment specifically has that cool side benefit.
Right, you mentioned biogas.
Yeah, breaking down organic matter without oxygen produces biogas, which is mostly methane. You can capture that and burn it to generate heat or electricity. A nice bit of energy recovery from waste.
That's brilliant, turning waste into power. So after these three stages, physical, chemical, biological, is the water usually good to go?
Often, yes, especially for discharge back into rivers. But sometimes, for drinking water or specific reuses, you need an extra level of cleanup. That's where polishing or advanced treatment comes in.
Going the extra mile for purity. What techniques are used there?
Several advanced methods. Membrane filtration is a really big one now. This uses superfine membranes acting like extremely precise filters.
Finer than the sand filters.
Much finer. You have different types like microfiltration, ultrafiltration, nanofiltration, and reverse osmosis, or RO. Each level filters out smaller and smaller things, right down to dissolved salts and molecules with RO.
Wow, so that can get water incredibly clean.
Extremely clean. Then there's activated carbon absorption. Activated carbon has this huge internal surface area.
Like in a Brita filter.
Exactly the same principle, just
Mm.
on a massive scale. It's great at absorbing trapping on its surface organic compounds that cause taste, odor, or color.
Okay.
Any others? Ion exchange is another. It uses special resins to swap out undesirable ions in the water, like hardness ions, or heavy metals for less problematic ones, like sodium.
Like a water softener, but potentially for other things too.
Precisely. And importantly, there's growing talk about needing a potential fourth treatment stage in some cases,
A fourth stage? For what?
to specifically target trace contaminants like pharmaceuticals or endocrine disruptors, chemicals that can mess with hormones. These are things that might slip through even advanced conventional treatment in tiny amounts.
Right, those emerging contaminants we hear about. That definitely sounds like a future challenge. Okay, this is complex stuff. Let's switch gears slightly. Who actually runs all this? How is the industry organized?
Yeah, the structure varies a lot globally. You find that most places have a kind of traditional setup that doesn't change super fast.
Who tends to own the pipes and plants?
Several models exist. Local government ownership, like through a city water department or public utility, is probably the most common worldwide.
Okay.
In some countries, especially smaller ones, the national government might own and run everything. Then you have private ownership, which is more frequent in certain developed nations. And sometimes you see cooperatives or even NGOs involved.
And what about running the day-to-day operations? Does ownership always equal operation?
Not always. Local governments might run things directly, sure, but they might also outsource the operations to a private company, even if the council still owns the assets.
Ah, okay.
National governments can run operations too. Private companies might own and operate the whole system. And then there are models like BOT, Build, Operate, Transfer.
How does that work?
A private company funds and builds a new facility, say a treatment plant, operates it for a set number of years, maybe 20 or 30, to recoup its investment and make a profit, and then transfers the ownership back to the public sector.
Interesting. So lots of different ways to slice it. What about splitting up the functions? You mentioned integrated versus separated earlier.
Right. So integrated means one organization handles, say, both the drinking water supply and the wastewater treatment for an area.
Seems efficient.
Can be. But separation by function is also common. Like the Dutch example. City does sewers, regional company supplies water, water board treats the wastewater, or Munich's three-way split. Separation allows for specialization, maybe deeper expertise in each bit.
But potentially more complex coordination needed between the different players.
That's the trade-off, yeah.
Okay. Now, water is so fundamental to health and the environment. I assume there are pretty strict rules.
Oh, absolutely. You have stringent water quality standards and environmental regulations pretty much everywhere, set at national or sometimes regional levels. It has to be tightly controlled.
Can you give some examples?
Sure. In the U.S., you've got the Safe Drinking Water Act for tap water quality and the Clean Water Act regulating discharges into rivers and lakes.
Okay.
The EU has major directives like the Urban Wastewater Treatment Directive and the Water Framework Directive. The UK uses its Drinking Water Inspectorate and Environment Agency. China has national standards like GB 3838-2002.
So specific laws and bodies overseeing things.
Yes, and there's even work on international standards through ISO CT 224 to harmonize best practices for water services.
A whole regulatory landscape. Okay, let's look ahead. What's coming down the pipeline, so to speak, in terms of water technology? What's the future look like?
It's a really dynamic area. The big push is towards sustainability and ensuring safe water resources for the long haul. One major focus is that advanced treatment for micropollutants we touched on.
The pharmaceuticals and endocrine disruptors.
Exactly. Developing and refining technologies like advanced membranes, better activated carbon, ion exchange, maybe even that fourth treatment stage will be critical to remove these emerging contaminants.
Makes sense. What else is big?
Water reuse and recycling? This is going to be huge. As water scarcity bites harder in many places, treating wastewater to a really high standard so it can be safely reused for industry, agriculture, maybe even indirectly for drinking water is becoming essential.
So closing the loop.
Precisely. It requires advanced treatment and very careful safety management, but the potential is enormous. We still don't reuse a huge percentage globally, but it's growing.
Seems unavoidable, really. What about the energy footprint? Treatment must use a lot of power.
It does. So energy-efficient treatment is another key trend. Finding ways to minimize energy use, maybe through smarter pumping, process optimization, or using more natural systems like treatment wetlands where appropriate.
And capturing that biogas you mentioned.
Absolutely. That anaerobic digestion producing usable energy is a perfect example of improving energy efficiency and resource recovery.
Good stuff. Any other key tech trends?
Well, we'll see more customized wastewater treatment, tailoring solutions for specific industrial waste streams or agricultural runoff or leachate. The focus is also shifting towards minimizing waste at the source within industries and recycling water within their processes.
More targeted, more efficient.
Yeah, and expect continued advances in membrane separation. Making membranes that perform better, last longer, cost less, and are easier to maintain is a constant goal.
Better filters, basically.
In essence, yes. Also, sophisticated adsorption techniques, improving activated carbon, finding ways to regenerate it more effectively, and developing totally new adsorbent materials. And finally, maybe more expanded use of electrochemical treatment. Things like electrodialysis or electrochemical precipitation for removing specific, tricky pollutants. The challenge there is often making them energy efficient and cost-effective at scale.
So a lot of innovation happening across the board, driven by efficiency, sustainability, and tackling new challenges like micropollutants. Now, just before we wrap up, you mentioned different types of treatment plants earlier. Could you just quickly list those again?
Sure. It mainly depends on what kind of wastewater they're built to handle. You've got your standard sewage treatment plants for domestic wastewater, often mixed with some pre-treated industrial stuff.
Okay.
Then industrial wastewater treatment plants, specifically designed for waste from factories or industrial sites.
Right.
Agricultural wastewater treatment plants for farm runoff and livestock waste. And leachate treatment plants dedicated to handling that contaminated water from landfills.
Got it. Each dealing with a specific type of challenge.
Exactly. Different pollutants, different concentrations, different treatment approaches needed.
Well, this has been incredibly insightful. To sum it all up, it's clear the water industry is this massive, complex, but utterly essential system. It's not just the tap water, it's the whole cycle of providing clean water and then managing wastewater responsibly.
Yeah, it involves this huge web of infrastructure, some really sophisticated treatment processes, physical, chemical, biological, advanced, plus diverse ways of organizing it all, and layers of regulations.
And the future looks really interesting, with technology driving towards greater sustainability, efficiency, and tackling those emerging water quality issues.
It really is remarkable how much goes into that simple act of turning on a tap or flushing a toilet. A complex system protecting our health and our environment, working mostly unseen.
It certainly gives you a new appreciation for clean water.
Okay, on that note, let's leave our listeners with a final thought to chew on. Considering these future challenges we've discussed, water scarcity, pollution, micropollutants, what role do you think technology versus our own individual actions and responsibilities will play in securing a sustainable water future for everyone? That's a big question. Tech versus behavior, or maybe how they interact.
Yeah.
Definitely something worth pondering.
Indeed. Well, that's all we have time for on this deep dive. Until next time, thank you for joining us.